but that's how important it is. If we get the framework of the tech assignments out the way for the first one, then it makes it seamless for the rest of them. Seamless. Okay. So the example here says transform matrix A into reduced row echelon form using, implied set of instructions using elementary row operations and your knowledge of the appropriate reduced row echelon form techniques. All right. The most commonly used technique is the idea of multiplying and adding. Scalar multiples is also a good one, but sometimes a good old switcheroo right off the bat gets the job done. So looking at this, my first thought is, this would be great if row 1 was row 3. So I'm going to use a biconditional and just say row 1 swaps with row 3. Well, it's not really a biconditional, it's just a symbol for a biconditional. It's just a double-sided arrow. All right, so I'm not going to color code this one because too much is changing. I'm just going to try not to screw it up. Now the reality is we actually have one of the solutions right away. So it's just a matter of working off of that to see if we can come up with the rest. But we're always looking for the obvious. I thought, or at least my brain took me in the direction that that was an obvious move. But maybe that's because I have a lot of experience with this. Maybe it wasn't obvious to you. Maybe your obvious move was to say, hey, I see multiples of 3 across that one row there, the top row now. So 1/3 of row 1. All right, so maybe that's where your thinking took you. Maybe you didn't do any of that. I don't know. It's kind of like, I don't know how much you remember from high school geometry class, if it was even called that when you took it, because for me it was sequential math course too. But it was proofs. You had to do geometry proofs. You had your given statements, and then you had, these two angles are the same by vertical angles are congruent and reflexive property and everything like that. And then from my students anyway, they always wanted an answer key. Like, can you give me an answer key for this particular problem? I'm like, what's the point? They're looking at that like, well, that's really defeatist. I'm like, no, it's not that I'm giving up on you. It's the fact that, like, I could give you like 10 different answer keys for the same proof, and there's a solid chance that none of them match what you did because your brain just took you in a completely different direction, right? So, that could be the case here. Maybe you didn't do any of this stuff. But these are the two strategies that, there's simple things that you can do, and if you can get them out the way early on, it's a worthwhile endeavor, all right? Because then eventually you gotta get into the meat and potatoes of it, and so that's where we're at now. But prior to that, at least you can kind of get the minutia out of the way, all right? So I'm looking at this and saying, okay, well, now I'll go back to the way we were doing it last time and say, let's make that 2 disappear. So I'm going to go, I'll keep it with red. It's fine. I don't have to go too crazy with this. So if I want the 2 to go away, I want to negate the 1 and add it to row 2. So negative 2R1 plus R2. So row 1 is going to stay put. 0, that's not red, 0, then 1. Well, that's nice. I wasn't going for that, but it worked. Negative 2 times 2 is negative 4, plus 0 is negative 4. Negative 2 times negative 6, well, okay. Negative 2 times negative 3 is 6, plus negative 2 is positive 4. And then we have our 0, 0, 1, 2. All right. So, again, just looking to just keep it going here. We have it in we have it in an echelon form, in that the leading entry in each row is to the right of the row preceding it, and we have zeros down below the leading entry, and just we don't have zeros everywhere else. All right, so if we want to get it into a reduced echelon form, we want to try to go the distance. All right, so, and that would be the pivot value, the leading entry in each row, in each individual row, should be the only non-zero value in that row. All right, I'm sorry, column. So basically, I'll circle them. I want these to go away. So if I could do that, we'll be golden. If I can't, we'll be bronze, I guess. I don't know where I'm going with that. So I could do something with row 3. I can act upon both rows 1 and 2 simultaneously. So we might as well do that. So negative 2 row 3 plus row 1, and then 4 times row 3 plus row 2. Take advantage of the old double move. Alright, so no change for the first 2 entries in either row, so that's good. The whole point of these operations is to zero out these guys. So I can just use that relationship to kind of get me where I need to go. So this is going to be a 0, 1, 0 with minimal thinking. And then 1, 1, 0 for the same reason. We just have to worry about the last column. All right. So I'm going to multiply row 3 by 4, so that's an 8, plus row 2 is going to give me a 12. And then I'm going to take the value in row 3 multiplied by negative 2, it's going to give me negative 4. Add to that a negative 3, that's going to give me a negative 7. Alright, so then we get to this point. We're done with row 3, there's nothing else I can do there. The only thing I can do to get rid of that 1 in the first row would be to negate row 2 and add it to row 1. So that would be my final step. And so we'll be looking at 1, oh, that's not red. 1, 0, 0, negative 19. Now, barring any catastrophic error here, that would give we were just looking for a reduced row echelon form, that would be our final answer. All right, because it wasn't asking us to do any more than that. But definitely something that you want to check, because again, this calculator is a useful tool, but sometimes again it could be a source of anxiety if it gives you not what you're looking for. So hopefully that's not going to be the case here. Let me see what I can do. When did I turn it off? That last one felt like it took about 10 minutes, right? I must have turned it off right after I did the problem. Yeah. Okay. Oh. I was hoping that I didn't accidentally hit it in the middle of the solution to the problem. No. All right. Phew, Jacqueline. All right, so just straight up negating row 4 and adding it to row 3. So 0, no change here, 1, -7. So then -7 plus 4 is going to be -3. And then you got to kind of take stock of the situation and say, okay, I know I definitely accomplished something. It's just a question of now where do I go? I know that at this point, because I have zeros in the first column everywhere except for that 2, that this is going to be my first row. All right, because my leading entry here is the 2, which I can easily make into a 1 by dividing everything by 2. But I got some odd numbers here. I don't want to mess with that yet. All right. So it's up to you. We can move that up now, or we can play around a little bit more, see what's going to happen, and then go from there. Like for example, I see that now I have 2s in the second row. Second column. So I can kill one of those. It really sounds terrible when I say kill, but that's really what we're doing. We're trying to kill them. We're trying to get them disposed of. Some cement slippers, that kind of thing. Yeah, I'm doubling down on this whole killing thing. Yeah. Yeah. I'm thinking like cartoon style. You know, like Wile E. Coyote just went off the cliff. Yes, exactly. Not the News 12 kind, you know. So I'm thinking let's impose row 3 upon row 1. So I'm going to say negate row 3 and add to it row 1, or add it to row 1. So everything's going to remain the same except for row 1. So I'm going to just chuck all that stuff in there before I forget and screw something up. So negate and add, negate and add. So it's 0, 0, 2. -7 becomes +7. Added to -4 becomes a 3. -3 becomes +3. Added to 1 becomes 4. And that's, as good of a byproduct that you could ever expect. I didn't go into this expecting that. It's my problem, so I kind of expected it. But I didn't go into this to orchestrate that to happen. You know, I went into this problem with the idea that we're going to try some operations, see how things go, and then go from there. So I have 2 identical rows. So I can wipe out one entire row. So what I'm going to do is I'm going to negate, my pen turned off. I'm going to negate one of them and add it to the other. It doesn't matter. So I'll negate row 1 and add it to row 2. or vice versa.
Why you have that 3?
What I would say it again?
Like the first one, like you have 0, 0, 2, 3.
In the first row, 0, 0, 2, 3, 4.
Yeah, why is 3?
Why is it 3? So if I negate the 7, it becomes positive 7, and then add it to the negative 4?
Sorry, I was working with the second one.
Oh, no, it's very easy to get it all crossed up with this. All right, so now we have kind of a plan of attack, and I didn't decide on that plan. It just naturally evolved, all right? Because reduced row echelon form tells us that any row that contains non-zero values has to be above rows containing all zeros, all right? So this red row has to go all the way at the bottom. So I know I have to do that. And then my pivot values in each row have to be to the right of the row preceding it. All right, so I have the arrangement. Right, I just have to rearrange now. Right, so this is something that I'm perfectly fine with you saying as a little notation, because generally, in all honesty, in most cases, the little notations are more for you than they are for me. Although I do need some way to assess your work, so it's like probably 60% requirement, 40% like your choice. You know, it's not like a 50-50 thing. It's like it's skewed more in the direction of it being necessary for you to do to get credit, but there's still an element of it where you want to do it anyway. All right. But what I would say here is rearrange. All right. Instead of saying switch row 3 with row 1, you know, like none of that business. I'm just going to write the rows where I want them to be. Because you could swap rows, so who's to say you can't swap a bunch at a time? All right, so it's looking pretty good now. I mean, I'm not going to say it's a work of art, but it's getting there. I can make that -6 go out, and I could do a lot of things, but I want to do the most convenient things first.
So what does rearrange mean?
So I move the bottom row to the top, this row to the second, just moving some things around. There doesn't have to be a convention to it. You could just do it in any way you want, as long as you take entire rows.
Why don't we divide them all by 2?
I toyed with that, but since I have some odd numbers in there, I was kind of hoping that would come out in the wash. Maybe some more of the odds would become even, and then I could make it a little easier on myself. So you could do that, but I'm going to hold off at least for another step or two. Because, like I said, I know I can make that -6 go away conveniently. I could also, I could make the 1 go away, but then I got to incorporate a fraction. So I'm gonna sit tight on that and see where my next step is gonna take me. So positive 3, R3 plus R1. So I'll reproduce all the other rows. And then put in row 1. All right, so first two entries are going to stay put to 0. Oh, this should be in red. Oops. So I need a TA. 0. That was the whole point of that calculation. 3 times 3 is 9, plus 9 is 18. 3 times 4 is 12, plus 7 is 19. So close. If only that were an even number, I could just chop that first row in half. But still, I could chop it in half right now if I wanted to. All right, so we're getting there. We're getting there. But it does look like I'm painted into a corner now where I do have to use row 3 upon rows 1 and 2 as much as possible until I've used it for all it's worth, basically, because nothing else is going to cancel out. All right. So if I were to use row 3 to try to cancel out the 18, all that's going to do is bring back a value here. You know, so if I did -6 on row 3, that's just going to introduce a -12 here, so that's not going to help. But what I can do is use it on row 2. So that's where we get into the whole fraction business. So it is what it is. We'll deal with it, but it's something that we're gonna have to tackle. We're gonna have to tackle it at some point. So now is as good a time as any, I guess. So I'm going to take row 3 and multiply it by -1/2 and add it to row 2. And then once I open that can of worms of chopping something in half, you know, like actually introducing a fraction, now fractions galore. We're just going to go crazy with it. All right, so rows 2 and 3 we're going to work on. Row 1 is going to be left alone for now. Three, 4, row 3 will be unchanged, row 4 will be unchanged. All right, so no change in the first 2 entries of row 2. The third entry, no, I said no change, not 0. The third entry should become 0 because that was the whole point. Then we have to do some calculation. And of course, try not to cough all over the place. That cough is still with me, it's killing me. So, -3/2 plus -7. So -3/2 is -1.5, plus -7 is -8.5. So we're talking about -17/2. And then -1/2 multiplied by 4, right, is -2, plus -3 is -5. So that's kind of clean. I'll take that. Call that a win. All right. So then we get to this point and we ask ourselves, is there anything I can do that's going to cancel out the 18 or the -17/2 or even the 3, right, without introducing non-zero values in the other columns, right? Because again, reduced row echelon form is telling us that the lowest rows should be your 0 rows, and then the rows above that should be the rows that have your pivot values. And those pivot values, again, the first non-zero entry in those rows should be to the right of the pivot value in the row above it. All right, that's checked out here. We'll make them 1s in a second. But they should also be the only non-zero entries in the columns that they exist in. True and true. All right, so this is in reduced row echelon form. Just because these last values aren't really amounting to anything that look like the way we want them to look, doesn't mean we did anything wrong. That being said, it's entirely possible we did something wrong, hence the ugly numbers, but it's entirely possible we did everything perfectly right and we still got ugly numbers. So we'll have to deal with this in a second, but let's do that last move of, now this matrix was not named, right? Okay. So I'm going to say 1/2, yeah, I'll just do it in black, 1/2 of matrix, call it whatever you want. Normally the standard is to say matrix A. Basically saying that I'm going to multiply every single entry in this matrix by 1/2. All right. Instead of saying 1/2 R1, and then 1/2 R2, and then 1/2 R3, and 1/2 R4, this is a simpler way of doing it. All right. So 1, 0, 0, 9, 19 halves. 0, 1, 0, negative 17 fourths. Negative 5 fourths, 0, 0, 1, 3 halves, and 2, 0, 0, 0, 0, 0.
Shouldn't it be negative 5 halves?
It sure should. Thank you. And so that's the matrix in reduced or echelon form. And it's very unsatisfying. But it actually gives us a meaningful solution. It just doesn't seem like it would be overly meaningful. So that's the next part of the fun. All right. So we're going to go back to the structure of the original problem, which was talking about the coefficient matrix associated with x1, x2, x3, x4, and then your solution vector, which was the 1, 4, 4, and 7. Right? So basically the first 4 columns are referencing x1, x2, x3, and x4. So we can actually put this back in the real terms that we were given and write some algebraic expressions. So the first one would be x1 plus 9x4 equals 19 halves. The second one would be x2 minus 17 halves x4 equals negative 5 halves.
17 over 4.
I keep doing that. That's so weird. Thank you. The third one would be x3 plus 3 halves x4 equals 2. Now the last one is really weird, right? And that's because there's nothing there. But we haven't really addressed what x4 is really equal to. So I'll show you here in a second. Well, that's the thing. You would think so because everything is 0. But what you're looking at in the last entry is 0 equals 0. So I'm just going to make a note of that. And then we'll talk about what that means in a second. But I want to go a little bit further with the first 3 equations. All right, the first one, if I solve for x1, x sub 1, what I'd be looking at is x sub 1 is equal to 19 halves minus 9 times x sub 4. Then we'd have x sub 2 is equal to negative 5 halves plus 17/4 times x sub 4. And then x sub 3 would be equal to 2 minus 3/2 x sub 4. So then the big question would be, we had 4 equations with 4 variables, right? There was 4 equations. So then the big question would be, okay, well, we've addressed x, 1, 2, 3, and 4, so what the hell is x sub 4 equal to? No. It's going to be equal to x sub 4. And the reason why is because of this statement right here. All right, if 0 is equal to 0, there was a complete cancellation. All right? And because of that complete cancellation, we end up with something that's infinitely true. All right? 0 equals 0, which means no matter what I put on either side of this equation, it's always going to be a true sentence. So if it's a true sentence, then if I put x sub 4 on one side, then I could put x sub 4 on the other side. Bottom line is x sub 4 is equal to x sub 4. All right? What we call x sub 4, I'll put a little notation here, is a free variable. All right, so x sub 4 could be anything. All right, it's completely free. All right, but the nicer way to write it would be to say that x sub 4 is equal to x sub 4. All right, instead of writing x sub 4 as a free variable. All right. So there's other ways to write this, and so what we have here is the beginnings of the parametric form of the solution to a linear system. All right. So, and this is why we start getting into the GeoGebra stuff. So you could look at this and say, all right, we did some math and we got some answers, and those answers, they look really cool. They'll impress people that are looking over your shoulder and wondering what you're doing when you're, sitting in a lounge and doing some math. But if you don't have a sense visually of what this is really talking about, it doesn't really do you much good. But I can write this a different way. I'll write it below, actually. Another way to write it would be to create a column that is the sum of the constants, so 19/2, -5/2, 2 and 0, because there's no the x sub 4, there's no constant there, so there's an implied 0, plus x sub 4 multiplied by the coefficients, -9, 17/4, -3/2, and 1. All right, so this is the parametric form. That's a very fancy sounding term. Parametric form is really just talking about you're establishing one variable as a parameter, meaning it is a variable that the other variables are defined in terms of. All right. So I would be saying that if I follow this relationship, I could then know what the values of x, 1, 2, 3, and 4 are. All right. But it's all dependent on what x4 is. Okay?
Yeah, I was gonna ask, would you want us to leave the answer in parametric form?
Sometimes yes, sometimes no. Down the line, we're going to do more with this, so then it'll be very clear when I want you to do one versus the other. Once we start talking about homogeneous cases and things like that, then it'll be obvious when I need this.
Okay.
But for now, you can go either way. especially since it's the very first problem that we did together related to this topic, I'm not going to get picky about which way I want you to write the answer. I'm thrilled to death if you can get either of these answers at this point. All right, down the line you'll need to get
So
one.
the negative for 17/4 or for 3
The negative. Yeah, so I'm just pulling the signs down here, so it should be
for the x over x down here.
down here. Yeah, I think these signs are right because they should be coinciding with these.
I take it. Okay.
Yeah, I'm just pulling it right down.
I take it from the.
Oh no, because what I did was I subtracted these over and that
You
changed
take
the
it
sign.
from the.
Yes. And I don't even know what I'm saying. So what I got in the habit of doing when I create my my visuals, sometimes I get lazy and I just grab it from the internet, and then sometimes I really sit down with GeoGebra and I create some nice visuals that I think are enhance the learning. And so example 1. Given u equals 2, 1 and v equals 3, 4, find w equals 3u and a equals 2v. All right. And then going through, and you can see the solution here. It's really weird. I don't know why I starred this one. I had this solution. Maybe starring it was my way of saying, really consider this before moving on to the other one. No, I just accidentally started, so sorry about that. So 3 times u gives you 6, 3. That's a scalar multiple upon u. And then 2v, scalar multiple upon v, gives you 6, 8. And you can see the size relationship has changed. One is double the length of the other. And then also, and one is triple the length of the other. But also, well, I said also, so I feel like I should say something beyond that, but really there's really nothing more to it than that. When you get into linear combinations and actually adding them together, there is an additional consequence, but since this was only talking about scalar multiples, I'm just going to leave it at that. Now, when we talk about adding vectors, the graphical representation is something very specific that I'm looking for you to demonstrate. So, and I will say, so I'm going to caution you on this, and I have the video recording my words, which means I have the evidence. So when you say I never said it, I can roll back the videotape and prove you wrong. So you're not going to be happy when that happens. All right? No, it's not going to happen. You're going to be fine. So on the test, which the date is listed in your syllabus. I can't remember. It's like the 5th. Or maybe the 4th. It's 2 weeks.
On Thursday.
On a Thursday. It's coming. But the first test is not designed to be the scary end all of the course. All right? Now, we just went over a problem that would make it seem like, okay, we're going to be at this for a while, but I mean, it was just addition and multiplication. So it's addition, multiplication, and perseverance. All right? That's the nature of the beast with this test. All right? Except when you get to this problem, because this problem I'm asking for a very particular approach, all right? So I'm going to detail that approach right now, and then you're going to star this, you're going to highlight it, you're going to make note of it, you're going to set reminders for yourself, all that good stuff. Because if you don't follow this approach on the test, you're not going to get much credit, all right? But it's a pretty easy approach, so you're not going to find you're going too far out of your way to get the credit. All right, so let me plot 2, 3. That's not the part that makes it hard. And let me actually get some tick marks in here. I'm just going to go crazy here. That is a triangle. That is not a tick mark. I don't know where that came from. That's so weird. Still a triangle. There's no reason that should have become a triangle. I'm just going to turn the line draw tool off. That's what I'm going to do. So 1, 2, 3, 4, 5 is good enough there. Maybe 1, 2, 3, 4. Yeah, that's good. So I'm going to plot 2, 3. Right about here. I'm going to draw a vector going to it. I'm going to call that U. 4, 1. Right about here. I'll do that in blue. I'm going to draw a line going there. Now, it says graphically find U plus V. You know that you could add these two vectors. You know that 2 plus 4 is 6, 3 plus 1 is 4. So you already know the answer, but this says to graphically find the sum of the two vectors. I'm looking for something very particular. All right? So what I want you to do is create a parallelogram out of these two vectors. Okay? So we're going to take this vector U. You can do it on your own paper very easily. Take the side of your index card, get the slope, and then shift it over till it gets to that point, and then reproduce that line segment. On that index card, make a little tick mark for the beginning and for the end. Shift it over. This is as close as we'll get to doing a construction in this class. All right? And then draw the line segment. All right? So you're going to make that ray. So for me, let's see, can I duplicate? I'm going to try it. Edit, copy. We'll see in a moment. Come on, give me a page. Okay, give me the whole thing. Okay, that's a complete undo right there. All right, but on my screen, it would be equivalent to taking that line segment and shifting it over so that it's over here. I'll do it as dashed.
Isn't the blue line supposed to be higher up?
Maybe?
No, it's not.
I mean, it's definitely 4-1 based on my crappy scale. Whether my scale is sufficient, that's a different story, because, you know me. I mean, maybe not, but you know enough to know that I have, my drawing abilities are suspect. All right, so you're looking at this line segment, do the same thing. Grab the edge of an index card, make little tick marks, get that slope, and then slide it on up. Draw a line segment representing a new one. It's going to connect and form a parallelogram. And then connect the opposite points of that parallelogram starting at the origin. And draw a new vector labeled U plus V. That new vector should actually terminate at 6, 4. All right, and you can verify that, but this is the work I'm looking for this problem. So when you really think about it in the grand scheme, look, I'm not really asking you to do much. You can even fake this work. Like you already have the two vectors. You gotta rough out a parallelogram and draw a line segment that somehow, some way gets you to the answer that you already knew going into the problem was going to be 6, 4, just by adding the two corresponding parts of your given vectors. Like the only way to screw this up is to not answer the question that I'm asking. Graphically find it. If you were to say, okay, 2 plus 4 equals 6, 3 plus 1 equals 4, and then do nothing else, you're sacrificing a lot of free points. All right. When I first put this kind of problem on my test, it was put on as like, they're gonna love me, this is gonna be like the greatest gift ever, and then half the class lost credit on it. I'm like, how could this possibly have happened? They're like, we didn't know what you meant by graphically. I was like, Well, when you wrote 2 plus 4 equals 6, fun fact of the day, that's not a graph, just so you know. And they're like, oh yeah, you're right. I'm like, yeah, I am. So, not asking for much. I'm not asking you for you to do this in 3D. Two dimensions is all I'm looking for. All right, so I'm keeping this light. All right, 3 dimensions it gets a little kooky. So honestly, this is right in my wheelhouse, in my artistic abilities. Like I can barely handle this. To draw something in 3 dimensions that'll actually look the way it's supposed to look, there's not a chance for me. All right, so I'm gonna reattach a star to number 3 because that problem, if you had no idea what I was looking for in number 2, that problem is now a little bit more user friendly. All right, so I'll leave that. Yeah, because the next page goes into. So you could keep adding dimensions. As long as numbers can keep existing, then dimensions can keep propagating. All right. So the general structure of it, and we have our unit vectors and things like that, but I'm not going to get into that just yet. The general structure is that you have an x-axis, a y-axis, and a z-axis. All right. Here's my x-axis, comes out the page directly at you, but it's really more of a perspective drawing. Then you have your y-axis, and then you have your z-axis. So when I'm plotting 2, 1, 3, I'm taking 2 steps in the direction of x or x1, then 1 step in the direction of y or x2, and then 3 steps in the direction of z or x3. All right. Freehand sketches are probably the best way to handle this, just because if you get too structured with it, then you feel confined by those structures, and that can be dangerous. All right, so it's one of those things where you don't necessarily know that that's going to be a thing until it happens. So you take this time to develop this carefully structured scale for your x-axis, y-axis, z-axis, and then you start trying to sketch a plane, and then immediately you realize that you're going to need about 17 more sheets of paper in order to fit that plane because there's no way it's going to fit on your scale. All right, so what I say is don't even bother with the scale until you figure out the characteristics of the graph. Otherwise, it's going to be game over. All right, so we want to get in the habit of thinking x1, x2, x3. So, like I said, we're going to take 2 steps in the direction of x1. Not going to plot a point. Just going to plot the steps, the tick marks, the relevant tick marks. Then 1 step in the direction of x2, and then 3 steps in the direction of x3. All right. These together, these movements together, are going to give us the location of the point in space. All right. So what I'm going to do, I have my 2 steps along the x1 axis. I am then going to make a movement consistent with the distance associated with the movement along the x2 axis, just from this location. All right. So what I'm going to do is I'm just going to make little dotted lines here. That distance is what I'm going to carve out to the right of the second step along the x1 axis. I'm going to go that distance. So basically the same index card approach I was talking about before, you're going to follow that here. Find this distance and then translate it down here, and then you'll have the appropriate distance away from the x1 axis. And then you're going to do the same thing with the x3 axis. You're going to take that distance and translate it down so that it gets to the tip of that outermost point from the movement away from the X1 axis. So this distance here, use your index card or 2 fingers and estimate that distance. And then plot a point at the end of the line there. And then this would be your point, 2, 1, 3. I'm just taking this distance here and translating it down here. So I'm starting off at 0, 0, 0. Then I'm taking 2 steps in the direction of x1. Then I'm taking 1 step in the direction of 2, which corresponds to this distance. So I'm taking that distance and putting it here, making a little mark to indicate where I am. So now I'm here. Then I'm taking this distance, the distance consistent with x3, and moving upward from there. So we're working with parallels. We're working with distances that are parallel to the given axes. The issue is that it's not going to look like square or rectangular movements. It's going to look like parallelograms all over the place. But that's essentially it. The idea is that this point is actually floating in space. It's hard to kind of reconcile that with what you see here because it looks like it's a point that's right next to this x3 axis, but it's not. All right? What you have to actually do is look at the corner of a room. I'll just take this little corner here. You have x-axis, y-axis, and then z-axis. So what happened was you took 2 steps, 1, 2. 2 steps puts you right here. Then 1 step out put you at this location, right where my foot is. And then 3 steps up. 1, 2, 3. So that point is right here. Okay? But how do you create a 3-dimensional drawing on a 2-dimensional diagram? You can do it. It's just it takes a practiced hand. It's not always going to look the way you want it to. And so the more practice you get with it, the easier it becomes. For me, you get that. That's why you use GeoGebra.
Why isn't y-axis the one that goes up?
Because the powers that be decided that's how it's going to be. It's so counterintuitive.
Yeah.
Honestly,
Like I see it, but I have to turn it around in my head.
my thinking is, if I have a blank piece of paper, I'll just hijack one of these. Nah, these are really nice looking packets. I don't want to do that. I'll just do this. So what somebody said was, you have on a piece of paper for all these students that have been taking math all these years, they've been writing x-axis and y-axis on that piece of paper, right? So if that's the case, then how hard would it be to just incorporate a z-axis? So then if you were to look at this piece of paper, depending on the angle that you take, you might be looking directly at the x-axis with the y-axis being sideways and the z-axis coming up out of the paper. But what they're looking at is, well, you've already been working with the x-axis and y-axis as a horizontal representation. So let's make z come out vertically because that'll be most consistent with the way that you've been working in pencil and paper. The problem with that is, yeah, that's how you do it in math class, but math class is limited to a small fraction of the amount of time of your lives. The rest of your time, you're experiencing 3 dimensions in a non-math class sort of way, where the z-axis takes on a variety of different forms. Length, width, and height. If I'm measuring the dimensions of a figure, if I were to tell you, give me the dimensions of that figure, and you were to say, the length is 2 feet, the width is 3 feet, and the height is 4 feet. And then I turn around to you and say, you know what, that's not acceptable. You transposed the length and the width. You said it incorrectly. No, I got the idea. because one dimension is a horizontal, the other is a vertical from the two-dimensional perspective, and the other is jutting out. All right, so you can say it any way you want, but the same idea comes across. My thinking, or at least my understanding, is that somebody decided, you know what, they'll understand it best if we use this approach, and it's just not. It's not the best approach, but it is what it is, and so here we are. Yeah, because it would be like, yeah.
Yeah,
Ooh, X, Y. Oh, that looks great. And then have a Z come out this way. You know, like, oh.
Or X2 could be Z, because I see Z as width.
Yeah. Yeah. I'll send them a letter.
So that is the final answer?
So that's the final answer. That's the graph. Yeah. And there's really nothing more to it than that, because when I create the vectors, all you're doing is plotting the points and then connecting them with a line segment. This one I got a little cute. I rotated my axes to give it a little bit of a better perspective, so it doesn't quite look like exactly like what we have up there, but it's the same idea. But let me take you, and this will be the last thing we do tonight, let me take you through a three-dimensional case and just show you how not well I'm going to create this graph.
So would this actually be an example of what we would do in the tech assignment, just not handwritten?
Right, that wasn't even close. Correct. And now I'm behind it. I'm going to give up on that for a few minutes. So, because obviously that's not working. So, yeah, this is not happening by hand because it's just a disaster waiting to happen. All right. So, I'm going to create my axes. I'm not going to put too much care into labels or anything like that in terms of the scale, at least until I get a sense of where I'm going with this. All right, so it's the x1, x2, x3 axis. And so the coordinates 1, 2, and 3, 1, 2, 3, but it's a vector, so we have to make a vector out of this. And then we have to find the vector sum, so that's a different story altogether. Okay, so I'm going to take one step in the direction of x1 along the axes. I do everything along the axes first. All right. You may decide when you get a handle on this, you want to do it some other way. I leave that up to you, as long as it comes out right. But this is how I do it. So at least give my way a shot before you decide it's complete garbage. I don't know. So I create tick marks as I go. And again, index card, a side of a sheet of paper. All I'm doing is I'm taking the length of 2 and translating it down so that the origin is going to go to 1, 0, 0. So this point here, my thumb is going to translate over to that, and we'll have a location to plot just an intermediate point. Right? It's not really a point that's going to be plotted. It's just to give me a sense of what's going on. So this distance here, I could use a pointer. I think, look at the old lightsaber out. So this distance here is going to get translated down here. And in some cases, we just eyeball it. In a lot of cases, we eyeball it. That's the real truth. You come up with what you think is the right length, and you do one of these bad boys. And I feel like a smidge more, maybe another dot. There we go. And then based off this scale, I need to go this many up. All right, from this location. So it's going to put me right about here. All right, so if I'm eyeballing it, I'm looking at something like right in this neighborhood right here. So I'm going to draw a line, a ray, to that location with a nice good looking arrow at the end of it. And I'm going to label that U. And that's on location 1, 2, 3. All right. Coordinates 1, 2, 3, but that ray is in space. All right. So again, this works out well because I have a graph at my disposal right here. I have a graph with tick marks and everything. So if I'm plotting 1, 2, 3, I'm going 1 unit in the x direction, and then 1, 2, 3 units in the y direction, and then I'm sorry, 2 units in the y direction, right? So back here, and then 1, 2, 3 units in the z direction. So my point is here, floating in space, right here, connected to the origin with a ray, and that's your vector, right? It's floating out in space, but it looks like if this were x-y axis, this would look like it's, you know, on the same plane as the xy axis, but it's not. It's kind of angled out, so it's kind of hovering in space, but it's hard to get that feel based off of the diagram. I guess if you kind of blur your vision and like tilt your head and maybe hold your breath for 30 seconds, you know, right before you start losing consciousness, it might actually start kind of coalescing into the right diagram. I don't know if it's worth that much trouble though. All right, so 0, 4, 1. So 0 in the x direction, 4 in the y direction. So 1, 2, 3, 4 units in the y direction, and then 1 unit in the z direction. So that's actually a little bit easier, because that's just going to put me 1 unit above because if you have a 0 value for x, you're really just living in the yz plane, the x2, x3 plane, all right? So if x is equal to 0, then your x2, x3 axes behave very much like your ordinary xy axis, over and up, all right? So that's kind of a nice byproduct, a little bit easier to work with. Now when I want to graphically find the vector sum, here it's just a matter of doing exactly what I did on the previous page, but you had to get here in order to do that. So this problem is a disaster to grade, which is why I never put it on a test. It's a nightmare. I mean, a wrong answer looks just as good as a right answer, so what's the value in it? I have people faking their way to full credit all the time. So maybe you want it on the test, but I'm taking this out and putting an easier one that you're all going to get right as long as you do it the way I tell you to, so what does it matter to you? All right, so I'm going to create the parallelogram using the same technique as before. Index card, eyeball, whatever. I came to grips a long time ago that there are some people in this world that can draw freehand better than I can with a ruler. So it is what it is. It's just the nature of things. So if that's you, go for it. I've seen some people turn in some work that I was like, man, you're good at math and art. Oh, you're so much better than I am. You know, like I get jealous, but then I give them 100 and we move on. So, you know, there's just some really talented people out there. When it comes to art, not me. Right? If I didn't have these tools to work with, I couldn't even do something this nice. All right, so create the parallelogram, draw the ray going from end to end, slap in a u plus v. Somewhere off on the side, tell me what u plus v is equal to. It should correspond with the location, but it's very hard to verify that. 1, 6, 4. I mean, honestly, if you could pick out in 3 space, if you could pick out the coordinates of a hand-drawn diagram of a point in 3 space with any kind of accuracy without like lots of stuff being given to you in terms of scales, then you're better at this than I am. You should teach the class, I guess, because it's not easy to do. Because the best you can do here is like say, okay, I think maybe we're 1, 2, 3, 4, 5, 6-ish, and then you get the 4, but how are you coming up with the 1? Like you'd have to make some educated guesses in there. It's not really something that would play out very well. So the best you can do when you're looking for a graphical representation of the sum is actually come up with the graph, but you're not going to be able to pull the answer from it. Whereas in 2 space, you can still pull the answer from the graph itself without actually doing the addition. So another reason why those kind of questions are better for a test. All right, so I'm going to put a star on number 6. Same idea as the previous page. You should be able to relatively easily handle